So again, I'd like to welcome everybody for attending the webinar today. Today we're going to talk about the application of the IEC standard IEC 61511 to industrial and power turbines. Take a look at kind of the trends and some of the issues that come up when that's done. So to introduce myself, my name is Chris O'Brien. I'm a partner with Exeter Consulting, and as many of you probably know, that we do quite a bit of work in the consulting and certification area related to functional safety standards. So I'll be your host today. What I'd like to do is I'd like to walk through how and when IEC 61511 is applied to turbine applications, talk about what's needed to demonstrate compliance with those with the standard and regulations, talk about different strategies for implementing IEC 61511, as well as some of the pitfalls that can occur, and then open it up for a question and answer time. So we'll get started. So I've seen in the industry some discussion about whether turbines should be treated under the machinery directive or the machinery safety standards or under the process safety standards. And where that really comes down, or how that kind of gets applied, is that for machine-related hazards such as crushing or burning, rotating pieces of equipment, the machinery safeguards and standards should be applied. So if the hazard fits the model of a machine, a classic machine hazard, then apply the appropriate machine safety standard. For hazards that are more process related, and those include explosion, overspeed, lube oil, and if you go to the accessories, drum level control, those types of things, then the process safety standard is applied, IEC 61511. And really, you can take a look at the operational mode of the safeguard as another indication. So machine guarding safeguards are typically in high or continuous demand operation, whereas the process-related safeguards, explosion, overspeed, are in low demand applications or operational mode. So that also helps give some guidance on where to make that decision. But it certainly isn't true that you would only apply the process standard or the machine safety standard to a device as complex and diverse as a turbine. Another kind of indication is there's a new API standard in development, or a new edition of API 670. It was originally thought that would be out last year, but I was just checking today, and I don't think it's been released yet. And there are key provisions that are being planned in there, including that API 670 will reference the IEC standards, both 61508, 61511, and 62061. I'll make a comment that tolerable risk is a function of the operating company and local legislation. Comment about the targeting of a SIL is a function of tolerable risk, equipment, and site specifications, and make a major focus on testing and diagnostics, and in trying to achieve as much automatic diagnostics through the entire protective functions, from sensing through the logic solver to the final elements, and document the speed of response as part of one of the requirements. So this, I think, will provide quite a bit of information and guidance to further clarify some of the questions that come up when people are applying the functional safety standards to turbines. There had been some discussion that, for example, in industry, well, all overspeed should be SIL 3. Well, that's not necessarily true, because it depends, as this third bullet says, what's the tolerable risk, what's the equipment, and what are site-specific considerations. So that'll be very beneficial when that is released. What we're seeing at Exeter is we're seeing pretty broad adoption of applying SIL to power turbines and to industrial turbines. And the things driving that are, we can start over on the left-hand side with national standards and regulations. Often, because there's natural gas involved in gas turbines, they're treated as high-hazard pieces of equipment. Or if they're an industrial plant, in an industrial plant or refinery, that plant is under is implementing these standards, so the equipment logically gets reviewed. There are competitive offers from turbine manufacturers showing SIL rating on the products. Application standards such as API 670 is further identifying and enforcing that. And then also the customer expectations, the expectations of the industry is getting more and more so that functional safety would be part of the offering on a turbine solution or a turbine refit. So let's talk about the steps necessary to demonstrate compliance to the IEC standards. So first, why is there a need for a standard? Why does it matter? Well, the standards provide a safer, or help provide a safer working environment for people, and hopefully eliminate injuries and fatalities. They help protect the investments in plant and equipment and ensure that they continue to operate, and that saves money. And thirdly, they demonstrate compliance with regulatory requirements and help operating companies avoid fines. How could a standard help do this? Well, it essentially documents best industry practice. So these standards have been developed over, years of time with lots of effort from different companies, identifying and documenting best approaches to problems. They provide consistency across organizations. They help OEMs, integrators, end users, EPCs can all work towards the same process and standard and have an understanding of what's expected. In a documented standard, it's less likely that you're going to miss a key step because by the nature things are written out and documented. And common mistakes or known problems are explicitly addressed. So, what's the safety life cycle? So if we take a look at the goals of the safety life cycle, it starts with hazard identification, essentially identifying what could go wrong through a process hazard analysis such as a HAZOP. Documents how bad it can be and how much risk reduction is necessary through SIL determination using techniques such as LOPA. Documents what needs to be done in the safety requirement specification. And then ultimately, last step before going into building is models how reliable is the proposed solution through SIL verification. And then through the life of the system, it maintains that high degree of safety reliability through the safety life cycle and periodic testing and refurbishments as needed. If we look at the safety life cycle in a more formal chart, we'll see we've got 3 phases: analysis, realization, and operation, 3 general phases. And then we also have supporting processes that are in play through the entire life cycle. So management of functional safety, safety life cycle structure and planning, and verification steps. These 3 vertical columns are done throughout the entire life cycle as support functions. The analysis phase is focused at, as we were just talking about, understanding what hazards there are, quantifying the consequence of them, determining if additional risk reduction is needed, and then documenting that in a safety requirement spec. The realization phase deals with designing the safety instrumented function and safety instrumented system, configuring it, performing factory acceptance testing, installing it, and then validating that it's ready to run. And then the operation phase involves operating and maintaining it, performing any modifications, and ultimately decommissioning it when the hazard is done or the process is done. These safety functions can have target SIL levels, and SIL, safety integrity level, can be used 3 different ways. So first, it's used to establish the risk reduction requirements, that is, how much risk reduction is needed. It's also used to set probabilistic limits for hardware random failure. And in a third way, it's used to establish the rigor necessary in engineering procedures to prevent systematic design errors. So what are the implications if a company is going to if a company is going to implement IEC 61511? Well, first, they have to use an appropriate SIL determined methodology, agreed upon methodology. The use of high integrity automated safety systems typically will be required as a means to protect against a given hazard. The need to intentionally separate both physically and electrically the safety system from the basic process control system. You'll need to complete periodic proof testing throughout the life of the system in accordance with procedures that should be set up during the design phase. And you'll have to have a documented proof that regularly scheduled reviews and were conducted per the applicable standards requirements. So many times these things are done, or they're done in a semi-formal way, and to fully implement the standard, you'll be looking at doing them in a well-documented formal way. Now, to show compliance for a given safety instrumented function, so let's say do the analysis and you determine, oh, we need protection for overspeed. That's obviously a very common hazard associated with turbines. And so to design a safety instrumented function for overspeed, you'll need to meet 3 criteria. The system, in addition to having an implemented functional safety management plan and safety life cycle, the given safety instrumented function will need to meet the SIL capability requirement, the probability of failure requirement, and the architectural constraints. So all 3 of those criteria must be met for a safety function to fully comply with IEC 61511. If we look at the purpose of those areas, of what they're designed to do, we can look at this chart. So SIL capability basically means that you have to have certified or proven in use for all the equipment used in your safety function. And the goal of that is to protect against a systematic failure in the devices themselves, so in the logic solver or in the transmitters or in the valves. And if there's an inherent systematic weakness in that design, you don't want that in your protective function. So the methodology is to use a certified product or do a proven in use analysis. Probability of failure on demand is protection against random failures, and the way you validate that is through the PFD average calculation. And then architectural constraints are another, they're considered a means to protect against random failures, and I kind of state it as strength against undetected failures. So if you have a high degree of dangerous undetected failures, you'll have a lower safe failure fraction. Or if you've got data that's not as vetted, you'll have a higher redundancy requirement. And the methodology of protection against about those unknown failures is architecture driven by the standard. So there are type approvals for equipment and steam turbines, gas turbines, HRSGs. So that's something that's been developed and implemented by multiple suppliers of equipment. Let's take a second and talk about what's necessary for effective implementation of IEC 61511. So often the first step would be a benchmark study leading to a gap, identifying gaps and a resolution plan. Development of a functional safety management plan would follow, then system design, implementation, operations, and maintenance. So let's talk about what a benchmark study would do. So many companies, and I'd say you can almost say virtually every company, whether it's a OEM supplier or it's an end user having a turbine, is going to have some procedure in place for the design, installation, and maintenance of those devices, devices being turbines. But if we wanted to have full compliance to IEC 61511, we're going to need to take a look at everything that's included. And what I've got here is just kind of a high-level summary of the phases or areas that the standard addresses. So overall safety management, the implementation of the safety life cycle that's compliant with the standard, and then as you get into that, you'll have a risk assessments, SIL selection or determination, documenting your hazards with safety requirement specs. Then we go into safety instrumented system design and safety integrity level verification. Once that's done, there's software design, software verification, and factory acceptance testing. Then the safety system will be installed and commissioned, validated, essentially saying it's been designed properly, installed properly, and commissioned properly. Then after that, we move to operations and maintenance, and again, modification and decommissioning requirements, and any documentation necessary. So there's some very specific areas that are called out in the standard that need to be reviewed and documented. We typically use what we call, we have a benchmark survey, a benchmark study, where we go through in detail the standard and the requirements of the standards, and review what's required by the standard and make the argument how it's met, or if it's not met, identify the gap and propose recommendations to close that. So that type of, to claim compliance to the standard, that type of review of the implementation and installation is important, because there are a lot of details in there, and without a systematic review of it, it's really impossible to say all the criteria has been met. Typical gaps that we've seen, there could be no structured process, or a semi-formal process, or a process that doesn't capture all the phases required by the standard. The second one is if multiple organizations are responsible. Let's say it's a new build, a new plant, or expansion, and one organization is providing the gas turbine, one organization is providing duct burner, one organization is providing utility boilers. If there isn't an agreed upon and communicated tolerable risk criteria used by all the different people bringing parts in to build the plant, the hazards can be targeted at different levels. There can be poor communication across organizations, missing or incomplete documentation, the use of non-SIL rated equipment for critical safety functions occurs. When the analysis is done, not all components may be included. I've seen things where the modeling assumptions done by, and this again goes to when things are broken down into, say, different organizations, the modeling of the initiating events for certain hazards are optimistic or incomplete. And another one is when there's shared equipment between maybe the basic process control system and the safety system, that can be modeled in a way that's too optimistic. So, key step is to establish a process, this is just a simple chart that shows the different steps going down the left-hand side, the different steps. And this is an example. Let's say there was a plant that had multiple pieces of equipment being delivered by different OEMs. So each of these phases need to be completed, and sometimes they're like safety management or proof testing. Those are going to be done at the plant level. There'll be a plant level procedure to control that. But there may be specific things in targeting hazards that relate to gas turbine that are different than what relates to the HRSG or the balance of plant. So often you might have individual groups or organizations handling key pieces of equipment, and clearly delineating the handoff and responsibility and procedures to be used across these, we can call them islands, is important, so that at the end of the day, when everything's integrated, the proper things have been considered and addressed in the right way. So establishing that process up front is very important. And it really, it saves a lot of rework. And sometimes if it's not done properly, it's really not practical to have a compliant project or plan at the end of the day. Typical V model for the development of the safety instrumented system would start with safety requirements. You do conceptual design, you do hardware design and software design, software configuration and hardware build, internal testing of the software, then integrate the hardware and software together, factory acceptance testing and site acceptance testing. So you see kind of a classic V here, which would be the V-shaped model. These small V's, these V's in the red circles, are verification steps. So between each phase, before you move to the next phase, and as you start integrating and coming back up on the V model, you validate, you verify that the goal, say in the software detail design, was achieved in the software actual implementation. Then you integrate, same with the hardware, then you integrate that all the way back up through the final system. Okay, so functional safety documents. Let's look at what some of the typical and required functional safety documents are. So I mentioned a functional safety management plan, and that's details the top-level requirements, competencies, levels of independence, roles and responsibilities. It should address all the phases of the safety life cycle, describe the handoffs between the phases and different groups, and may contain the definitions that would be used in a specific project. A group procedure could be a procedure that relates to a relevant specific phase and defines inputs and outputs required. And the project plan would be the tracking document for each project: who, what, where, when, and how, including sign-offs. So you might look at it this way. So there's a functional safety management plan. If required, there's going to be procedures. So we have the analysis, design, and operation and maintenance phase. So for those phases that are going to apply, so maybe if you're delivering a plant, you're going to just go through the analysis and design phase, and then operation and maintenance is going to be the requirement of the ultimate owner. Or if you're the owner, you're going to own operations and maintenance, so you're going to need those internal procedures, and your functional safety management plan is going to include a review of the planning and procedures of your suppliers. So for an entire, say, site to be compliant, all of these issues need to be addressed, but they can be broken through different organizations. So by looking at the phases that apply, the group procedures, you can then create the project plan that would reference the procedures, and also assign out the ownership of them, or the ownership of the phases. If we look at some of the, so one of the pitfalls we were talking about, or a typical gap, would be no structured process. So you can see by having these different procedures and plans, they put structure in the process. They, for example, we talked about not having an agreed tolerable risk. Well, that would be spelled out in the SIL selection plan. An approach like this improves communication across organization, and it also improves the likelihood that all communication or necessary documents would be done. Another common area that's missed is using non-SIL rated equipment for safety critical applications. IEC 61511 says that all equipment must be assessed per IEC 61508 or justified based on proven in use. And 61508 applies to, as we probably all know, automatic protection systems, and they're basically written as electric, electronic, or programmable electronic, but it doesn't just apply to the electrical parts of the safety system. It applies to anything in that safety function necessary to achieve a safe state. So it applies to valves, it applies to actuators, and this is a little excerpt from, from the IEC website, but it applies to sensor through control logic, communication systems to final actuator, and it may even include human actions if necessary. So it's important that everything that is in one of those safety instrumented functions, whether it's a purely mechanical device or it's an advanced TMR controller, either be assessed to 61508 or the user does a proven in use analysis. Now, proven in use is an acceptable method, but it basically places the burden on the user of the equipment to justify that it's SIL capable, and it may be difficult to collect meaningful statistical information. And if it's SIL 3, if anything is SIL 3, it requires a formal functional safety assessment to 61508, which is really not practical. So it may be practical for mechanical elements such as valves on a SIL 1 or 2 application, but it becomes harder and harder if software is involved or you have a SIL 3 application. But fortunately, more and more OEMs are providing, equipment OEMs are providing SIL certified product, so that's easier to address these days. Another shortfall that we've seen quite a bit is people will market compliant systems, but they're not looking at the entire loop. They might be, the red shows, the red and the blue shows kind of typical breakdowns of what we've seen promoted as SIL compliant turbine systems. So sometimes it's only the safety PLC, and sometimes it's the sensor, PLC, and trip lock, but not the valves. We actually did a little study and looked at 7 manufacturers that were marketing SIL 3 turbine systems, and you can look down here. None of them. Let's look at it. So the first one, SIL 3, they had 2 out of 3 sensors, a SIL 3 certified PLC, but they didn't include the trip lock or final element. So that would not be a complete system. Same with manufacturer 2, same with manufacturer 3. Manufacturer 4 went through, had a 1 out of 2, didn't specify the PLC, but had a 2 out of 3 trip lock configuration, but didn't include the final elements. Manufacturer 5 had the trip lock, showed a 2 out of 3 final element configuration, but one of the valves was a control valve. So there's an issue there with sharing equipment, so typically in a turbine application, say for overspeed, failure of the control loop can cause the hazard. So including the control valve and the protective function without some additional calculations is optimistic. And again, you can see, on these marketed SIL3 solutions, they're not well vetted. They're not complete, and they're not well vetted. Another problem that we see often in analysis is unrealistic modeling assumptions. So one is assuming 100% proof test coverage. Another is not accounting for mission time, and another is not accounting for common cause failures between redundant architectures. So 100% proof test, here's an example of a final element group with 100% proof test. So essentially, if you tested it once a year, your PFD average would go up, your PFD would go up through the year, then go back to the initial point after every proof test. And that gives you an optimistic PFD average, because what really happens is with an imperfect proof test, which is typical, you're going to, depending on your mission time, your PFD average is going to continue to get higher, and your risk reduction will get lower. So here's an example of 2 identical sets of equipment, the same equipment. One is modeled with 100% proof test coverage, and it gets a risk reduction of 184, and another is modeled with a 70% proof test coverage, and it gets a risk reduction of 28. So you can see there's almost there's over an 8-to-1, or about an 8-to-1 difference in actual achieved risk reduction. So if your proof test includes a leak test across the valve and a timed closure, then you're going to be achieving 98-99% proof test coverage. If your proof test includes a partial valve stroke or a full valve stroke of the valve, you're going to be more in the 70% coverage, 70-80% coverage range. So the design of those tests is very important on the overall achieved safety of the system. Another thing that I alluded to before was modeling shared components. So on turbines, especially, since isolating either steam or gas is often the solution to the hazard, or the way to avoid the hazard, and there can be multiple paths for the gas or multiple paths for the steam, including the safety shutoff valve and the control valve in the analysis can be appropriate. However, there's a couple different methods to do that. The first one is if we say don't take any credit for valve redundancy. Since the control valve can be the initiating event, we're going to say it can't be claimed in the safety function. Now, that's very conservative and may lead to costly designs, because you're going to wind up having to put additional valves in. Method 2 is to assume full redundancy and kind of discount that the valve could be an initiating event. That can lead to very optimistic designs, because there is a reality that the valve can fail and be the initiating event, and when that happens, it can't be counted on as a protection layer. A third method is to assume what we would say partial redundancy, and consider the initiating event of the actual failure rate of the valve, the actuator valve assembly, as a additional initiating event that only has one valve, only has the safety valve. In this example, we're using 2 valves, only has this safety shutoff valve, and for all other initiating events, assume that you have redundancy. And method 4 is the same as method 3, except in the standard it says to model basically 0.1 probability of failure of 0.1 per year for the basic control system to be initiating event. And then method 4, we do the same thing we do in method 3, but we pull out the failure rates of the actual valve assembly from the 0.1%. So if we look at the system we might be talking about, we have this graphic. Where here we have a steam turbine. We have a basic process control system that's controlling, say, the speed. So we're looking at speed sensors, BPCS, positioning the steam into the turbine through a control valve. Then we have a safety instrumented system sensors to a safety instrumented system to a safety valve that can isolate the steam. So typically the configuration would be is that the safety system de-energizes both the safety valve and the control valve on an overspeed. So we can model that as one independent layer and then a shared layer. So the sensor, the logic solver, and the safety valve are independent from any initiating events, but the control valve is shared between the initiating events and the safety function. To model that, so the method that we recommend is method 3. So let's say in this case the only initiating event was the basic process control system. So there we're going to take an initiating event of 0.1 failures per year times the PFD average of the safety instrumented system function with 1 out of 2 valves, and we get an intermediate event frequency of, shown here, 7.69 e to the minus 4. But because the control valve that we counted up here could also be the initiating event, we basically go and say, well, what's the failure rate? If we look at the part of the function that is shared, what's the failure rate of that function? That turns out to be 0.02 failures per year. We look at the PFD average for a 1 out of 1 protective function, which is lower, significantly lower than the 1 out of 2. We get another intermediate event frequency, and then we can add them together and we have the total outcome frequency. And this chart shows kind of the results of the different methods. This was method 1, where we can completely ignore the redundant valve, and you see you get a relatively low risk reduction factor, and it's constant. Method 2, where we treat them as purely independent, count as a 1 out of 2 valve assembly, we get an optimistic model. And then method 3 and 4, and we recommend 3, they basically track, and you get somewhere in between. And if we look down here, as the probability of failure of the actual control valve assembly increases, meaning its unreliability increases, you can see its ability to help protect in any of these configurations goes down, which makes sense. So, here's the 0.02 we were looking at. If we didn't count it, we'd probably be down around 30. We counted it, we got around a risk reduction of 70. If we double counted it completely, we're probably up around 140. So it gives a good example of, you don't want to ignore it completely because that's too conservative. You don't want to neglect the fact that it can be a contributing factor because that's too optimistic. So you want some reasonable methodology to model the fact that it sometimes, many times, can help prevent the problem, but sometimes it actually causes the problem. So for system design, for good system design, you want to select SIL-rated equipment when possible, make provisions for as much automatic testing as you can, and that can be a diagnostic or it can be an automated proof test. So maybe on shutdown or startup of the turbine, you can do certain checks of valves or other equipment. You want to consider if there's certain rebuild times or refurbishment of the turbines or subsystems. Are you able to model that mission time is longer than the total mission of the turbine? So maybe the turbine's going to have a life of 25 or 30 years, but every 5 years or 10 years you're going to rebuild certain parts of it. You can model those parts as having a shorter mission time. And then you want to use modeling tools that correctly capture and model all variables. So, for example, and one thing I always have to warn people is if you look at the informative parts of IEC 61511, I think it's section part 3, they have some simplified equations, but they're only simplified equations that don't fully model the system. So you want to, whenever you're modeling, you want to be sure that the tool you're taking or using takes into account mission time, startup time, architectural constraints, common cause failure rates, Exodus supplies Excellentia, which many companies use, but you either want to do it through a fault tree or something like Excellentia and properly model everything, and you'll get good detailed results. So for implementation, you also want to ensure all parties clearly understand their roles and responsibilities. For example, does the system integrator have a software specification and a software validation plan? That's required under the standard. Is the safety PLC physically configured per the OEM's requirements for a given SIL level? We've seen that where there may be a SIL certified PLC and there's a safety manual that goes with it that says here's how you need to implement it for it to achieve SIL 2, and people don't implement it that way, and at the end of the day they don't have a SIL compliant system. Is the delivered PLC code exactly the same as the FAT code? So if you do an FAT and you use that as a key verification step, and you're going to reference that in the functional safety assessment, which is a wise thing to do, is the code that gets to site the same code that was reviewed at the FAT? And if there's been a change, what impact analysis needs to be done, and verification or revalidation needs to be done. And then also be sure to perform a pre-startup functional safety assessment so that requirement of the standard is met. In operations and maintenance phase, it's important to control the access to the safety PLC configuration. Any change has to be made via a documented process and tested and validated before it's put into place. It's important to perform and document all the required tests, and that can be proof tests, and follow up on those issues or any diagnostics that are enunciated. Be sure that they're corrected. Confirm that rebuild, if you're taking credit, let's say you have a 30-year mission time, but you're taking credit that every 5 years or every 10 years you're going to rebuild a certain part of the system. Make sure that they occur, because the reliability model won't be correct if they're not. And then identify and correct any systemic component issues. If you're having early failures or higher failure rates than expected, it's probably an indication of a systematic problem. So addressing and correcting that is critical. So what I'd like to do now is see if there's any questions. I think we can do audio as well as Q&As. So we have some time left. Now we have recorded this, so we will post that. So any questions? Again, and my email's at the bottom, so feel free to send me an email as well.
Hello?
Hello?
Yeah, Patrick speaking here. Hi, can you hear me?
Yes, I can.
Yeah, I have a question, and I must say I'm really not expert here starting with this topic, but I had a question to you, was on slide, I think, 25 or so.
Okay, let me go.
there is this proven in use concept, and for non-seal rated equipment. So that means, or let me help me if I'm correct, if I have a system which I need for Seal 3 application or certified, so do I need to assess the components according to IEC 61508, or?
It actually says that in 61511, when you're at the SIL 3 level,
Yeah.
it says, it's hard to read in this slide, but formal functional safety assessment per IEC 61508 and the creation of a safety manual. So it makes it difficult. What type of equipment is it? Do you have a specific item you need, or?
Well, that is a combination. That is hardware, like sensors, and software. So that, as I understood, that's really, really complicated to get some CO3 certification for that, because it's, let's say, not very easy software. Well, it's not easy programming, not very simple functions. So you have to put something in, figuring out how that.
Now, is this? Are you configuring the PLC, or is this? Are you using a safety rated PLC for the software, or is it embedded software? Kind of.
No, with the PLC that wouldn't work because there are more functions or mathematical functions in which you cannot program in a PLC. So it's a question if you would use an FPGA or.
Okay.
But so still, we would need to require, let's say, get an assessment after 61508.
Yes. Yeah. And I have seen some turbine controllers that have been now. And assuming that these functions are protective functions, they're not control functions; they're protective functions, right?
Protective function.
Mm-hmm. And I've seen companies do like their control systems with FPGA and get that IEC 61508 certified.
Mm-hmm. So you mean
that is more the approach.
An FPGA that would be certifiable to CO3?
The implementation, yes.
Okay.
Yep. Oh, yep. Absolutely.
Mm-hmm. Okay, that's good news.
Oh yeah, and in that case, 61508 for that work is the appropriate standard because the specification, the development of the code, the programming of the FPGAs, the testing of it, and all that. That's more in the 61508 equipment manufacturer realm than it is in the 61511 implementer or user realm. So that, yep.
Okay, thank you.
All right, my pleasure. And please shoot me an email if you want any other information or want to talk about it. Okay, and I'm looking. Okay, and looking at some of the questions that were written in. So, what's the level of awareness of OEMs? From John, I'd say it's getting better. There are some that are pretty aware and have gone as far as getting some of their even turbine certified, and there's others that are somewhat aware. What about, and here's another one from Edgar, what about final elements being motor starters? And have we seen SIL-rated mid-voltage MCC applications? I have seen applications that require the motor starter to be successful. I'm not aware of any SIL-rated ones yet. So I think your question is a good one because often maybe starting a pump or stopping a pump or de-energizing an electric valve or something. So I think the motor starters definitely apply, Edgar, but they're not. There's probably 50 or 100 valves certified. I'm not aware of any motor starters yet that are certified. Here's a question from Sahul. How do you manage frequent proof testing of overspeed trip tests?
Thank you. Bye.
Okay, so frequent, I would say the most I've kind of seen people plan would be once a year. But the question he has is that sometimes industrial turbines run 3 to 5 years continuously, similarly for varying temperature trip. So you have to model that test as every whatever that test interval is going to be, you have to model that as whatever that time is. So if it's 3 or 5 years between tests, then that's what you have to put into the calculations, which can drive down the risk reduction factor. So you might have to put in a means of improved diagnostics. So maybe you could do comparison between the speed sensors for that, and maybe, on the trip valves, though, you could do a partial valve stroke test, but obviously you can't close the valves unless you've got enough capacity through, sometimes there's multiple streams. If it's a steam turbine, maybe there's 2 or 3 paths in to a particular pressure phase, but you have to model it and see if you can achieve it, and that's the key, and that is often drives improved diagnostics, or the need for better diagnostics to do it. Oh, I just see Ted's commenting there are some certified intelligent motor control devices and drives on the market. So back to the question from Edgar about final elements. Ted's making a comment that he's aware of some, so that's good. So that would be a solution. There's a question on slide 21. Oh, on slide 21 about certifying. So balance of plant. So this would be like a 61511 assessment of a plant. So there might not be, you could go to the extreme where in the balance of plant there were no SIFs, but in certain countries, Australia specifically, the authorities are looking for assessments and evaluation of the installation. So ensuring that the procedures that 61511 was applied, that a HAZOP was done, that hazards were identified and mitigated as necessary, would be part of looking at the balance of the plant. Or if the auxiliary boilers were in the balance of plant scope, then, or let's say, for example, there were auxiliary boilers, then you would look at those. So it's not that there'd be a 508 certificate or a standard certificate for balance of plant, as there would be, say, for a gas or steam turbine, but in a plant review, just that you would look at those and make sure that was done. Those are great questions. Thank you. Other questions? We still have a few minutes. Again, as I was saying, that feel free to send me an email or give me a call if there's other questions. We still have some time. I mean, I'm available now. Okay, well, if there's other questions, we'll post the webinar, and everybody will get an email. I'll look at a PDF copy of the slides, and also a link to the recording. So thank everybody for participating and for their questions. And if there's anything else we can help you with, let us know. Okay, thank you.
Thank you.